Good afternoon all. It's come up to just past 25 past 12, and so I would say that we're good to start. I think there's still people signing in, which is absolutely fine. 13 so far. Thank you once again for sort of tuning in, and I hope you find this useful. We'll start in the usual manner, please. So I'm going to put 3 minutes on the clock. Today's title is this, the motor effect and Fleming's left-hand rule. First thing I'd just like to do to check very quickly is I just need to confirm for me that you can hear me well enough. The second thing I need to do is introduce us to my cat who just barged in through the door. She may well be part of the lessons as we go forward because she hates a locked or closed door. I think I'm getting confirmation you can hear me. Just let me know if you can hear me well enough. Excellent. And yeah, this is my cat. This is Rags. She is more or less your age. She's 14, nearly 15 years old, and she is wonderful. But yeah, she doesn't like a locked door, so if she ever barges in, that is something we will put up with. So off you go, Rags. Yeah, 3 minutes of silence anyway. So let's put that on Dreamski on the clock. And off we go. Could we please have the usual jobs done? So make sure you put that title, and the title is a long one, but it's The Motor Effect and Fleming's Left-Hand Rule. If you can't see that, I'll just bring this a bit closer. As well as updating your content. So if you want a My Class, that's in the back of your book. Ignore that if you're not on a My Class. In 3 minutes' time, I'll also ask you some questions about last time, so have a think and a read back over that. And I'll also ask some general physics questions from stuff you have learned over the past couple of years. 2.5 more minutes, thank you. Yes, I did, Matthew. I'll respond to that in turn. Yeah. Rags is now standing all over the equipment. She is a pest. Just realised the time's being obscured by the cat. You've got 20 seconds left. Well, that's the time. I'll make Rex say goodbye for now. Say bye, Rex. Rude. Never mind. I'll put her down. And we'll start with some recap questioning. And what I thought I'd do is I'm first going to ask some questions from longer ago. That will probably make them harder. And the last few questions I then ask will be from yesterday to make sure you understood some of the key facts of that. I'm going to ask one question from each of the physics topics you've covered in GCSE. So starting with a question about energy. And the question is, and I'll pick someone to answer, so it's not a race to answer this time, it's just someone I choose specifically from my list. If they're not here, I'll have to choose someone else, so we'll give them a minute in case they are here. But the first question I'm going to ask is this, from the energy topic, what is the law of conservation of energy? What is the law of conservation of energy? And I'm going to give that question to Emma. Law of conservation of energy. Emma's answered, and hopefully you can all see that energy cannot be created or destroyed, only transferred. Perfect definition. That's the law of energy. Second question I'm going to ask is from our second topic, electricity. I'm going to draw two circuit symbols and ask someone just to say what they're the symbol for. I'll bring it close enough to the camera. Person being charged with answering this is Holly. Now, I'm not sure if Holly's in today. She was yesterday. Those two circuit symbols, if you can. Thank you. Now, I hope I'm not acting too hastily. I can't see any sign that Holly's in, so in this case, could I just ask for a quickest answer? The name of these two circuit symbols. Anyone can now answer. Excellent. We have got the right answer from Max, and we have the right answer from Emma. We have that it's a thermistor, the one on the left, not a variable resistor. Common mistake there, but unlucky, the person that got that wrong. That is a thermistor. That one, a fuse. Well done if you got them right. My next question from the world of particle model of matter, that was topic 3. And the question I'm going to ask is a definition of something. I want to know what internal energy is made up of. So all objects have an internal energy to them. And I want to know what that internal energy comprises. That question to Harry. And I've seen that Harry's in, so Harry should be able to answer this. What is internal energy? A tough one to remember, but let's see if you can. What is internal energy, Harry? Harry has said it's the kinetic energy and the potential energy in the particles. He's absolutely right. So it's the movement of the particles themselves. In a solid, they vibrate. That is a form of kinetic energy that even an object that appears to be still like this has. All of its particles are vibrating. And between each of those particles exists a bond. And that is a store of potential energy. So internal energy is kinetic energy plus potential energy. Well done. I'm going to now go to some more recent stuff. So they were the first 3 topics of physics, and maybe in our next lesson I'll ask some questions from other topics. So my next questions focus on stuff from yesterday. And the first question I'm going to ask, again, involves me drawing something just quickly. I'm going to draw a wire, and I'm going to draw the wire looking like that. And around it, I'm going to draw a magnetic field. Because as we learned yesterday, there was a circular field around a wire. But my question is, in what direction should I be labeling those arrows? I meant to say before, try this with your book shut. It's very easy to look back. Try it just from memory. The question is going to go to Jasmine. So Jasmine, could you tell me whether I'm going to be labeling the arrows clockwise or anti-clockwise? Clockwise. Thank you, Michael, by the way. Sorry, you'd answered before I'd said it was Jasmine's question, and you got it right as well. But so is Jasmine. Well done. It will be clockwise. And remember, that is from this right-hand rule, where the thumb represents the current, and this means it's going into the page. So thumb goes like that, fingers naturally curl in that direction. And as we're looking at that, it's really well done. Just a couple more questions. I do like to recap and make sure that we've understood the basics of what we need to know. I am going to draw a solenoid, and I'm going to mark on it the field. Slightly less complete diagram than the one we did yesterday, and slightly rushed. I apologize for the quality. but we have a solenoid and we have a field around a solenoid. And I'm going to mark on direction of the arrows. And again, I'm going to choose someone at random to answer this. But I'd like to know whether north is on the left of this diagram or north is on the right of this diagram. Is north on the left or is north on the right? And that question going to, I think that's someone who's nodding. Emily. Is north on the left of this diagram or north on the right? That question to Emily. Emily's answered right, and she's answered with a question mark, I think, at the end, indicating she wasn't sure. Remember that, Phoebe, yes, you are in the lolly sticks in answer to your question. But remember that when we look at the outside field, not the field inside the solenoid, but the outside field lines go from north to south. So in this case, north is here, south is here. North's on the left of this diagram. Field lines going from north to south. I hope that's clear. We are going to move on now. So I'm going to teach you something new. I'll be teaching you today about the motor effect. And let me just advance this a little. And as I did yesterday, I'm going to start with some demonstrations. And I'll try and tell some of the story of where this came about. So remember where we were at. We had that Hans Christian Ørsted had almost accidentally proved that whenever a current flows through a wire, there's a magnetic field around that wire. And for a brief time, as with any discovery, there's a sense of, well, what can we do with this? Of what possible importance could this be? That was in 1820, exactly 200 years ago. Well, through the next few decades of that century, the development in this field was huge. And we have a number of people to thank for that. But one of my favorite scientists is one of those people, Michael Faraday. Michael Faraday showed how you could take what Ørsted had found at the time, and it involves the exact same technology that Faraday uncovered. But even in the more simple things, I'm running this stream off my laptop, and to keep cool, it has a fan. It has a motor. Motors are in so many devices that we don't even consider. They are a massive part of our technology. And I'm going to show you now what the motor effect is and how it was discovered. So once again, I'm going to be moving the camera around. Just bear with me for a moment as I do so. Right. Certainly from the feed that I can see, you've got a really good view of this now. So hopefully you'll be able to see what I'm pointing at. What we have here, I'll just bring this a little closer first. At the moment, we are looking at something where there is only one magnet present. And it's a horseshoe magnet. It's all one color, and we're used to magnets being a combination of red and blue. This is just all one color. It's just in the color of the metal itself. But you might be able to see an N and an S marked on this. So it is one magnet, but it curls round. It is in a horseshoe shape. You can just about pick out that it's in a horseshoe shape there, I think. So it starts there, comes around in a horseshoe, and down here. North is on the bottom as we look, south is on the top. But what we've also got is a nearly complete circuit. Currently, this circuit is incomplete, but I will show you it when it's complete. I'm just going to untangle these wires so we can see things as well as possible. So what we have is a power pack providing the power source for the circuit, set to 6 volts this time, a bit higher than what I was using it for yesterday. And we have an incomplete circuit. Currently, the current flows through this first wire here and through this wire here back to the power pack. We have an incomplete circuit. When I turn this on, no current would flow. Piece of wire. And I'm going to put it there. So now we have a complete circuit. We have a circuit that flows out of this wire from the power pack through here, through this piece of copper I've put on there, and back through to complete the circuit. A current can now flow. So right now this is off. There is one magnet in this picture. But what you're about to see is when I turn this on, there will suddenly be two magnets in the picture. And this wire, which is free to move, and remember, by the way, copper is not magnetic normally. So I'm touching this to the magnet and it's not being attracted. I'll compare that to a piece of steel, which is absolutely attracted to the side and sticks to it. So copper cannot be permanently magnetic. But as we learned yesterday, the moment a current flows through that, it will become a second magnet. And we'll go from having one magnet in this picture to having two. And we'll see what the effect is. So I'm now just going to turn on the circuit and we'll see what happens. The answer seems to be not much. That worked better than that on the, there we go. There's just a slightly dodgy connection. I'm going to do it again so that you can see it and see it properly. Just had a slightly dodgy connection to sort out here. I think it is working now. So once again, with my hands out of the way of what you're seeing, I'm going to turn this on and it should work better this time. Oh, nearly. You might have seen some sparks come off that too, because when, again, this is technically a short circuit, there's nothing for the power to be dumped onto like a bulb or anything like that. So the whole thing heats up and sparks are created. But watch again for a third time. So right now there is one magnet in the picture. The moment I switch this on, there are two magnets in the picture and we get an effect. One more time, because it is working a bit more temperamentally than normal. That is the motor effect. What you're seeing right there is the motor effect. It's the idea that when you combine a magnet with a current carrying wire, that wire will experience a force and it will move. That technology there is the basis on which all motors are built. Well, there's one last thing about this I'd like to show you, and it's if we now reverse the current. So I'm now unplugging and replugging in the two wires. So before you saw that the that the wire rolled that way. Now when I turn it on, although you can see it's been a bit temperamental so far, it should roll this way. I'm glad that one worked a bit better. That is the motor effect. I'll say it again out loud, but we will make notes of any of this. That is the idea that when you have a permanent magnet and add to it a current carrying wire, you place a current carrying wire in the magnetic field of that magnet, that wire will experience a force and it will move. And that is what motors are built on. Well, I'd like to show you one other thing, just while we're talking about the motor effect. Faraday discovered that, and that a number of people had already discovered. The genius of what he managed to do was he managed to puzzle out how we could turn that effect into spinning rotary motion, something that doesn't just move one way and stop, but constantly spins. And the simplest way I can show that, although I'm going to warn you, it works about half the time, is with a fairly simple set of ingredients. This is a strong magnet. This is a battery. So as I combine the two of those things, I have the ingredients for what I need for the motor effect, or most of them. I have a magnetic field because of that battery, because of that magnet. I'm going to have the potential for a current to flow because I have a source of voltage in the battery. So now I just need something to connect it all up. What I'm going to do, and like I say, this has been nothing if not temperamental this morning, is I'm going to use a piece of blue tack just to hold this all nice and still. I'm going to hold the camera once it's up and running so I can zoom in and show you what's happening. All I'm attaching to the top is a nut, and that is just to make sure that the last thing I add doesn't fall off. The last thing I add is a curved piece of wire. There are gaps here and there are meant to be, sorry, there are gaps at the end of this wire and there are meant to be. It's a loop of wire designed to fit over the top of this. And what we should see, if I do this right, is the wire spins. We've created a simple motor. I'm definitely not showing that well, am I? Bear with me. It's almost happening too fast to see, but I'm going to try and show it from the side as well. Hope you can see that that wire is spinning and spinning really well. So that is how. Now Faraday didn't do it with a battery. Batteries didn't exist. He used some mercury and he floated away in the mercury and it spun around. But that was Faraday's genius. He realized how to turn the effect we saw just before with the sticks into rotary motion. Now there is a payoff here. This battery will be getting really very hot by now. And the batteries, it does wear out the batteries. So if you try it, do be careful. It does make the batteries hot and you have to then get rid of the battery. But we're getting the motor effect to produce rotary motion here. So one last time, I'm just going to say the key thing we've learned so far today, which is that when you combine a magnetic field, like from the magnets down there, and you add in a flowing electric current, a current carrying wire into that magnetic field, you can see it's almost run out of juice now. But when you add a current carrying wire into that magnetic field, it will experience a force, and that force can lead to motion. That is the basis of the motor effect. And that's the first thing we're going to write about now. We're going to write some notes. I'm just going to undo all of that so it doesn't carry on staying hot. So once again, I'm moving about and we're going to make some simple notes together. You will need, for this first bit, just a pen and a ruler probably. A ruler is just going to be for underlining as well. So, a subheading, I think, please, to start. I'm just checking if there's, oh, there are some questions on the basis of what you've just seen and some really, really good ones as well. So I'll pause there. Max asked, if you had a bigger battery, would it spin faster or anything? And the answer is absolutely. It turns out there are 3 ways you can increase this motor effect. And an equation will teach us how in a moment. Absolutely. James, I think, asked a similar question. He said, there would be more current, wouldn't there? So I think so. He's trying to answer Max's question. And absolutely, the first thing that the motor effect depends upon is the amount of current that flows. We'll add all 3 things and talk about them in the form of an equation shortly. But our first note is a simple sentence about what the motor effect is. So, subheading, please. And I'm just going to adjust this to make sure that we can see the whole thing on screen if I can. And just going to make sure it's also super sharp and focused. Right, I think that will do. So a subheading, please, the motor effect. And yeah, my writing's a bit slower than normal when I'm working in this pen. I'm sure you'll happily bear with that as I do so. So underline that, that is a subheading. And we'll write what the motor effect is now in a sentence. And it starts something like this. When a current carrying, and I'm hyphenating that, current carrying, when a current carrying wire is placed in a magnetic field, when a current carrying wire is placed in a magnetic field, comma, it experiences a force. It experiences a force. Full stop. That there is the motor effect. So it's the idea, and you saw it in 2 different ways there, that when a current carrying wire is placed in a magnetic field, it experiences a force. A couple more questions came up as well. So Phoebe asked, where do you get the twisted wire thing that was spinning? You can make one. All you need is just, and if you go on YouTube on some other videos, you'll see some really interesting examples of variations on that. But all you need is a stiff enough piece of wire to hold its shape. You can get them in most hardware stores or B&Q. Thin piece of wire that's thick enough to hold its shape. Piece of copper, ideally. The magnets are the hardest thing to come by, but there are websites that sell strong magnets. They're called button magnets. And then just a normal battery. Anything else I did, like the nut and the blue tacker, just so that it all works well. But yeah, the ingredients to make one of those magnets are easy to source. Max asked, oh no, Max answered. Yeah, it's just a piece of copper wire twisted like that. So sorry, the question had already been answered. I should read ahead before I start answering the questions myself. Back to the motor effect then. First thing to learn today is the motor effect. And it's when a current carrying wire is placed in a magnetic field, it experiences a force. Well, physicists like certainty in things like this. And so after some studying, it was found out that actually a simple equation governs the size of that force, the size of the motor effect. So another subheading, please. Motor effect equation. Motor effect equation. The notes we make today are going to be much more concise, and we're going to be getting to the work phase of the lesson rather more quickly today. But there isn't much to write, really. First thing we'll do is we will write it in words, and I'm going to struggle to fit that in, so you're going to have to bear with me. But we'll write it in words, then we'll write the symbols, and we'll define the units too. We'll do this all nice and thoroughly. So the equation has as its subject the force. The motor effect is all about the force that comes out. And it's dependent on three things, and watch where I write these to fit them in. The first thing it's dependent upon is the magnetic field strength. Times by, basically it's times by the length of wire. It's times by the length of wire you have in the field. So in the example you saw before, this length of wire is what you put into the equation. This length of wire governs how much motor effect will be felt. And so the last variable in this equation is length of wire. And I'm going to put length of wire in field. The length of wire that is actually within the strongest magnetic field. Well, in symbols, you can see I much prefer this equation in symbols. There's simply less to write. It's quite a nice, memorable one. Force is capital F. Magnetic field strength is B. And yeah, when equations spell out words, they're somehow more memorable. And so F equals Bill is one that people do tend to remember. Finally, I'm going to add in a row beneath what each thing is measured in. So force, and I'm using square brackets if you're not taught by me, just to show these are units. This is something different. Force is measured in newtons. And in fact, in the margin, I'm just going to write units, if I can fit it in with my pen. So force is measured in newtons. Magnetic field strength is measured in something called Tesla, named after Nikola Tesla, who did a lot of work in this early magnetism field. So if you want to write underneath that is Tesla, you can do, because that's a unit you might not be familiar with. Current is measured in amps. And again, if you'd forgotten, because it's a long time since we did electricity, no harm in writing amps there. You can write newtons there if you want, for completeness' sake. And the length of something, always in physics, we will revert to lowercase m for meters. So when you're using that equation, force is measured in newtons, magnetic field strength is measured in Tesla, current is measured in amps, and the length of the wire in the field is measured in meters. F equals Bill. That is the motor effect equation, allows you to work out various things about a system of that sort. Well, there is one last trick I want to teach you, and it's something called Fleming's left-hand rule. And again, I'm going to blast straight through with this lesson. We're going to carry on with the notes so we do them all in one sitting. So I'm going to change my piece of paper. I'm going to check there aren't any extra questions. Oh, there are, but I think they've been answered as well. So yeah, someone asked, did he make the Tesla car? No, he didn't. A living inventor called Elon Musk started that company. But he absolutely named the car in honor of Nikola Tesla, who was one of the great scientists, one of the great geniuses, sadly ended penniless and ended his life in difficult circumstances. But his contribution lives on by the fact that various things are named after him. Yeah, he was a real pioneer in the field of magnetism and of electricity. And he was not left-handed as far as I know, but I don't know that for sure, Gerald. Anyway, Fleming's left-hand rule next. So could you write the subheading? Fleming's left hand, and I'm hyphenating that again, left-hand rule. And actually, I said I wouldn't do any more demonstrations, but I am going to go back to one of the demonstrations we saw before. So once you've written the subheading, Fleming's left-hand rule, that's all you need to write for now. I'm just going to bring our attention back to the first demonstration we saw. And it will allow me to practice Fleming's left-hand rule with you, but of course we'll make all the notes we need to as well. Right, so remember what we had. We had this idea that when a current carrying wire is placed in a magnetic field, it will experience a force. And with them connected as I've got them now, it should roll towards this direction. Let's see. Well, Fleming's left-hand rule allows you to predict what will happen next. To use Fleming's left-hand rule, and we're going to practice this a number of times, but to use Fleming's left-hand rule, you have to have your fingers in this slightly strange configuration. So I've got to make sure I'm on screen when I do this. I don't use these two fingers at all, and it just uses the thumb and the first two fingers of the hand. And I'm holding my fingers at 90 degrees of the trio. Is it 90 degrees to them both as well? That's making 90 degrees, and when we look at it from the right perspective, this is making 90 degrees as well. So all three fingers are at right angles to each other. There is a posh word for that in physics. It's called orthogonal. If things are all at right angles to each other, they are orthogonal. But in Fleming's left-hand rule, you take your left hand and you arrange it like that. And each of these fingers represents something. The thumb represents the direction this is going to move. We're going to use this as our prediction thumb in a moment. But let's look at the other two. This represents the direction of the electric current. This one represents the direction of the magnetic field. So in our example here, let's make sure we know what direction everything's happening in. First, let's make sure we know the direction of the magnetism. North to south. So when we're using our Fleming's left-hand rule here, this finger, because that represents the it represents the current, will point that way. This finger, because it represents the field, will point north to south, point upwards. The current itself is flowing out of the red side of the battery bag of the power pack by convention. It's coming through here and through in that direction. So as it passes through this, the current is going that way. So remember, the field pointing upwards, the current going that way. I'm really struggling to keep this on screen, aren't I? I promise you will practice this a bit better and on screen. But the field was pointed upwards. The current going in the way that my second finger is pointing. And that leaves my thumb pointing backwards. It leaves my thumb pointing in the direction it actually rolled. So just to go through those again, and we're going to need to go through these a few times for people to pick it up. I'm certain of that. First finger here is the motion. The thumb here is the motion. The first finger is the magnetic field direction. and the second finger represents the direction of the current. I'm going to line these two up, and we'll see what direction my thumb points in. So first, let's line up the magnetic field north to south. That's why this finger has to point upwards. My second finger has to represent the direction of the current. Now, the direction of the current here, this finger is the current. This finger is the magnetic field. So the magnetic field, this finger has to point upwards. The current is already doing what it's meant to be doing. I'm pointing that way and the current was flowing that way. And that left my thumb pointing towards that direction, and that predicted the way it would roll. I wouldn't be surprised at all if you are really quite confused at the moment. I'm just going to show it for the opposite case now, which will involve less twisting around of my hand. So now I've reversed the current, but everything else is the same. So second finger's current. So now the current is going that way. I can line that up. My first finger represents the magnetic field. That still has to point north to south. And when I do that, you can see that leaves my thumb pointing in the opposite direction to before. My thumb is now predicting that this will roll that way. And it does. It's known as Fleming's left-hand rule. We're going to have to draw a left hand now, and you know my track record on things like this. We're going to draw a left hand and label what each means, what each finger means in this rule. And then we'll also practice it a couple of times before you try it for yourselves. So, underneath our heading Fleming's left-hand rule is one of my most ambitious diagrams to date. I am going to attempt to draw something that looks a little bit like this. A left hand with a thumb pointing upwards, a first finger pointing to the right, and then as if coming out of the page, and it's always hard to represent a 3D diagram in 2D, as if coming out of the page, the second finger outwards. This could go terribly wrong. You might want to watch what I draw before I draw it, before you draw it rather. So that's the thumb. So far, not bad. First finger field has to be going at 90 degrees to that, like that. The second finger, we're going to have to draw as if it's coming out of the page. Now, there's going to be no convincing way to do that, except to sort of show that it's trying to point outwards, some sort of perspective on that. That's terrible, but I can live with it. And then the other two fingers tucked away, not playing any part in this. Right, and we're going to label what each of these represents. I'll just finish off the hand. Do it like that, so we can see the wrist going off in that direction. I am not proud of what I've just drawn, but it will be clear enough for what we need to do. So try and draw something like that. You're trying to draw something, basically a hand in that arrangement. The thumb upwards, the first finger going to the right as you look, and the second finger pointing out of the page towards you. Not easy to do. I'll give you a moment to do that. And we're going to label what each one represents. Do you know, if I was clever, I'd have made you print off a picture of a left hand for this, but we'll manage with what we've got. I'm now going to start labeling what each of the bits means. So this first bit was the thumb, and so what I'm going to write is thumb, and underneath I'm going to write what it represents. It represents the force, and in brackets I'm going to say it represents the motion, because most of the time we're talking about the force leading to a motion, but that thumb represents the force. The first finger represents the magnetic field, so I'm going to write field. The second finger, the other one that's important here, that second finger represents the current. And that is Fleming's left-hand rule. You can use it to make predictions about the physical systems that you are studying. You can make predictions about how the motor effect will work, when you have a piece of wire and a magnetic field. Could I ask you to, now I'm just going to keep that on screen a minute and check for any other questions. I can't see any others, which is fine. I'm just going to give you a moment to sort of make sure you've caught up on the diagram. Sorry if you're absolutely caught up. Just want to make sure I'm not leaving anyone behind. It's hard to tell from in here. Right. Shout at me by commenting if I've gone too fast here, but I'm about to put something in the way of that diagram now, but I'm hoping people have had time to copy that out. Could you have this sheet in front of you? It was one of the ones I asked you to print out. We're going to practice 1, 2, maybe 3 of these, and then I'm going to leave it up to you to see if you can make sense of them. So first one we're going to do, we'll do together. Second one, I'm going to ask for your predictions by typing your prediction. But we're going to look at question 1 first. Now I'm hoping that your copy you can have in front of you if it looked a bit too small on the screen. What we have is an arrow showing the direction of a current, the direction of a wire in a magnetic field. And we have the field itself created by a north and a south there. So we know that the field goes from north to south. We know the current is going like that. Let's align our hand using Fleming's left-hand rule to this diagram. Now I'm reaching around the camera, which makes this all the more awkward. There is a good chance I'll knock it off at some point, but I'll see what I can do. Right, second finger current. I often start by aligning that one first. I'm aligning it in the direction shown there. But you can see my magnetic field is pointing in the wrong direction naturally now. It's pointing from south to north, and it needs to be pointing from north to south. And so the whole thing, I'm going to have to just rotate my whole hand. Come off screen to do that for a minute. And when you do that, I'm now lined up properly. My second finger, you can't quite see what I'm doing here. Still can't. But my second finger is aligned up with the current. First finger with the magnetic field, and it's leaving my thumb point downwards, pointing downwards. The answer to the first question, and I'm not quite sure on this sheet where we should write it, so I'll just write it here, is that F, the force, is down or downwards. I'm going to now show you question 5 as well. On question 5, you can see what we've got. We've got a field going from north to south as we look on this page. We've got a current going to the right. And actually, I'll give you a moment to see if you can predict for me the direction that that piece of wire will experience a force. I'm going to give you a moment and look for answers to appear on here. So use your left-hand rule, line up the correct finger for current, the correct finger for the magnetic field, and tell me in what direction that will experience a force. Answer by commenting. Max, you asked a good question there, and I'll come back to that at the very end of the lesson. There is a reason, and it will require a little bit more detail. So there'll be a point in the lesson where people can go if they want, and I'll answer your question then. If I forget, remind me, and I'll do it next lesson. But at the end of the lesson, I'll answer your question. We've got 2 answers in. We've got Emma and we've got Anna. But we're looking at question 5. And first one I'm going to do is line up the current, and that's correct. So you can see the current is pointing to the right. My second finger is pointing to the right. But once again, my magnetic field is pointed in the wrong direction. On the picture, it's going north to south. It's going that way. But my finger is naturally pointing that way. So I've got to move the whole thing around, and that's where you end up sort of twisting yourself in knots here. But when I do that, the answer was down. The F, the force, is down. Well, there's perhaps one last one I want to just show you, just to remind you about notation. So this one here, number 10. On number 10, we have got a wire that's now coming out of the page. You can imagine the wire pointing up like this pen is. So there's a wire with a current coming out of the page and a magnetic field like that. Well, let's try and align our hands to it. So firstly, let's line up the current. The current's coming out of the page, so this finger now pointing upwards. But the magnetic field, once again, I've got wrong here. It should be going from north to south in the opposite direction to what it is doing right now. So I move my whole hand around, and now they're both lined up. You can see that my second finger representing the current is pointing upwards. My first finger representing the field is pointing downwards, and that leaves my thumb pointing to the right. This wire would experience a force in that direction. So in this case, the force is to the right. Now I'm about to give you maybe 10 minutes or so to try these. There are 2 pages of them. Over the page, the diagrams get complex, but these crosses represent the magnetic field. So on this one, which is called A, for example, the magnetic field is into the page, the current like that. On this one, the magnetic field's out of the page and the current's like that. If you have any questions at all, please do ask. I'll be monitoring the comments. But the first thing I'm going to do now is, having taken this off screen, which I'll do in just a moment, I'll stand here with a timer, and I'd like you to take 10 minutes to try and go through some of these, and we'll see how you do. So, as I move the camera around, and let's have 10 minutes on the clock, please. So I'll keep more or less quiet, but I will be monitoring your comments and asking questions and trying to answer your questions. 10 minutes, try the rest of that sheet and see if you get the hang of this Fleming's left-hand rule. That's a great question, Max. Max asked, what if there are multiple magnetic fields? Well, you can imagine that this rule of thumb, almost literally a rule of thumb, um, wouldn't work as effectively because this rule only allows for one direction of magnetic field. What I would say is actually that in the way fields combine, you could always end up with knowing one overall direction. Like we talked about resultant forces, you can have lots of forces on an object, but they all add up to be one overall force. And in the same way, if you have multiple magnetic fields, they would theoretically all add to be one overall size and direction of field. And so you could still apply the rule, but you'd have to do some work to find the overall direction of the field. And actually, modern motors do that. Modern motors, we're going to learn about the motor either next lesson or the lesson after. Modern motors aren't just one north and one south. There's often at least three surrounding it. So they're coming in from three different directions. And so, yeah, Fleming's left-hand rule becomes difficult. And the other thing to say, sorry, there's a slightly rambling answer. The other thing to say is this rule clearly only works when you have 90 degrees. So when the y is perfectly at 90 degrees. If you do A-level physics, you'll learn a little tweak to the F equals Bill equation. And a little tweak to that equation allows you to account for different angles, and so you can use the equation more generally. This only works when all the angles are 90 degrees. You've just had over half your time. There's 4.5 minutes left or thereabouts. Just keep working. I'm sure you're all working brilliantly. I'm absolutely getting that impression today. Three minutes left. Just over a minute, and just under a minute's time, we'll go through this. I hope I've given you about the right amount of time. That's difficult when there's not the feedback of the room. I might have given you far too long or far too little time, but we'll start to go through them in just over 30 seconds. Done. We'll go through this now. I think I'm already thinking that the second piece of work we're going to save for another lesson. So once we've gone through this, we'll be very near the end of this session. I'm just conscious that we've reached our hour mark just now. And so I don't want to keep you well into a second hour. So we'll go through this and then we'll do some things to wrap up, and that will be it for today. I'll put the rest off until next week, but I'll say more on that in a minute. Let's go through this one first. So once again, I'll just be moving the camera around and about. Now, on this one, please don't despair. One of two things is likely to happen with this. You'll either get them all right, or very likely, if you don't get them all right, you'll get them all wrong. And it won't be that you are a terrible failure if you do. It will be that you're mistaking one thing about it. There's a thing with the left-hand rule is if you get one part of it wrong, then you end up with the opposite answer to what you were hoping. So, on question 2, we had, and I will go through them quite quickly. Some of them just especially early on, I'll go through in a little bit more detail. But we had a direction of current in that direction. We had a magnetic field that is making my finger point in the wrong direction right now. The magnetic field should be pointing to the left, not to the right. So I've got to rotate that around. And that leaves my thumb pointing down into the page. Your first answer, and well done if you got it, should be that the force was down. Question 3, I'll go through in less detail. When the pictures change, I'll go through more detail. In picture 3, you should have found that this wire would experience a force upwards. Question 4, also you should have found that the wire will experience a force upwards. Now, if any of these are wrong, there's every chance when I've been going through these in advance that I have made a mistake. Please shout up through the comments, but I'm going to assume I'm right. I took some time to make sure I was getting them right. Question 6. We'd have to describe the wire as coming out of the page. And so I was probably a bit loose in my wording before we went through, and I shouldn't really have described this as down. I should have described it as into the page. I meant down as into the page, but it's better to use the phrase into the page just to show you again on question 5 why that would be the case. The current will be pointing that way. The field will be pointing that way, and that leaves my thumb pointing into the page. Always be careful with your wording, and sorry I misled you there. On question 7, it's another into the page. Question 7, into the page. Question 8, out of page. These little notes here were not part of it, and sorry if they confused. So out of page there. On question 9, it was to the right. And we did question 10, which was also to the right, the force to the right. On to the second page, and the notation changes somewhat. Again, this stuff in the middle is just guidance. The pictures end there, and I hope that was not too confusing. But on A, up was the answer. On B, and B is the one over to the right here, down was the answer. On C, up. On D, down. On E, left. On F, left. Max has just asked a question. I'll just answer it as we're here. I'll just pause there for a moment. Max has said, if you were giving something like that in an exam, would into the page, out of the page be the answer they are looking for? Absolutely, it would be. So on that example I did before, I wouldn't have got the mark. I said down, and I knew what I meant, and hopefully you knew what I meant, but it wasn't clear. Down would appear to mean that way on this, and I meant into the page. So yeah, you always describe it as being into the page or out of the page. Absolutely. On to G, and the answer is to the right. H, also right. I, now the answer is diagonal here, and it's diagonal left, so towards the left bottom corner. I'll answer with an arrow there. It's diagonal into the left bottom corner, and J is diagonal towards the right top corner. It will go in that direction. Two slightly different ones to finish. Well, I'm going to ask one thing of you. And in fact, I'll turn the camera back around because we can do some closing remarks. At least we can once I've got it all adjusted. So that was the motor effect, Fleming's left-hand rule, and how to apply it. I think there's a very good chance you'll either have got that completely, especially the left-hand rule bit of it, or you'll have made the same mistake again and again. And what I'd like you to do is, if you were one of those second people, if that was still making absolutely no sense to you, please email my school email. I'll reply in the rest of today. But the other thing we'll do to start next lesson is we'll absolutely make sure we practice some more of these. And many of the practice questions, I'll have them on screen, and we'll practice as a class using the left-hand rule, because it is tricky. A good time to end the lesson. We never got to that second sheet, so here's my instruction for now. What we're going to do is we're going to carry this idea and this topic on into the next lesson. The beauty of doing our lessons at the moment is we are not constrained by any time limit at all. So we'll do this next lesson. The next lesson will be next Thursday. Do some more examples. We'll go through what I think are some Fleming's left-hand rule examples. We'll go through what I think are some really interesting questions. You can do them in advance if you want, but there's kind of no point. You can wait till that time. But if you want to have a bit more time at them, you can work at them in between times. But we'll then give some time to go through the question, and we'll review the question. And I think that in itself will make another nice hour's lesson. So for now, well, two things. If you want to stick around, I'm going to say my goodbyes in a minute. But Max asked the question earlier, and I'm going to provide some more detail as to why it's up, or why it's down, or why it's left, or why it's right. Why the left-hand rule works as it does, by drawing a slightly more complex diagram. If you want to see that extra detail, stick around. But what I'll say for now is goodbye for now, if that's all you want. Take care of yourselves, take care of yourselves through this week, and carry on doing the right thing even when it's tempting to go out and socialise. Make sure you stay in and do your bit. You only need to look at the news to see what kind of crisis we are still in. So make sure you do your bit and make sure you stay safe alongside your families. So bye for now. Look for emails about what's going to come next time, and see you on Thursday of next week. Bye for now. And if you want to stick around now, I'm just going to show you an answer to Max's question. Once again, I'm going to move the camera around, and I'm going to have to leave the room because I'm going to need to employ the use of a second colour of pen. So just one moment while I do that. we have a third colour of pen as well. So I'm going to work in 3 colours of pens. I'm just going insane at the moment. This won't take long, by the way. If you stuck around, it really won't take long to go through. But I just want to answer Max's question, which was a really good one, and answer it in more detail. So I'm going to use this, and I'll probably set the camera down again, like when we do some notes, and talk over it in that way. Should have got a bigger board rubber as well. Oh well. Right. So yeah, Max asked a really good question. I am just going to turn the camera around and attempt to answer it. Right. I think so. It's slightly a jaunty angle, but I think you'll be able to see what I'm doing. So yeah, Max, you asked a really, really good question. Why does it end up that way, or is it just the way it happens? Well, I hope this diagram goes some way to answering your question. We're going to see a lot more of the invisible fields than I showed in our diagrams before. So what we have there is the end of 2 magnets, or one of those horseshoe magnets, but we have a north meeting a south. And when a north meets a south, you get a uniform field between them. We looked at that in our second to last lesson when we were still in the classroom. But you get a uniform field existing between them, like that, north to south. So far, there's only one magnet in this picture, and it's creating a field going from north to south. This could be 2 ends of 2 different magnets, but it's essentially one field, one magnetic field. Well, the motor effect is all about what happens when you introduce a second magnet into the equation, an electromagnet normally. And when you have an electromagnet, and I'm going to draw one in now, I'm going to draw a wire that is going into the page. Well, we know the field a wire has. So remember, we can use the right-hand rule to find the size and shape of the field around this wire. It will be circular, like this. We know that much. And from the right-hand rule, we know that the field will point clockwise as we look. So what we have are 2 fields interacting. But now take a look at the arrows. What we've got is over the top of this wire, we've got a strengthening of the field. We've got arrows lined up together. These 3 arrows from this line up with these 3 arrows from this. Over the top of that wire, we have a strengthening of the field. What we've got down here is a disappearing of a field, because we've got field pointing this way and field pointing that way, cancelling out. So now I'm going to redraw the overall field that you would have left. The overall field that you'd have left, I'm going to have to rub this off, will look something like what I'm about to draw. So once again, yeah, we had, and I'm going to leave the fields off this time, we had a north and a south. They created that uniform field. We introduced into that gap a current carrying wire, current going into the page. And like we saw, when we did that, we had the fields adding to each other there and working against each other here. So our field picture would end up looking something like this. Over the top, there'll be a really tight magnetic field. Over the bottom, the field had cancelled out because the ones pointing left and right cancelled out. Fields are vectors and they cancel like any other vector quantity would do if they're going in opposite directions. And that means this wire experiences a push from the top, but not from the bottom. This wire would experience a force downwards. We can use Fleming's left-hand rule to prove it as well. So north to south is the field, first finger field. Second finger is the current into the page, and our thumb points down, same direction as that arrow. So I hope Max and anyone who stuck around for this, about 9 of you still did, I hope that explains the extra detail to the question that Max posed. The real reason is the way that the fields of the two objects, the magnet and the current carrying wire, the fields of the two objects interact together. And when they interact, they produce a resultant field, which means that wire experiences a push in a certain direction. So I think that will do us for now. If you stuck around, thank you so much for that extra bonus content. I'll reiterate the same thing. Tune in again on Thursday, but also look out for your emails. I'll tell you details and anything else you might need to print. I don't think there will be anything. Take care of yourselves. Bye for now and have a lovely day and a lovely weekend coming up. See you for now. Bye.